that is why our geometric datum did not move. And this is why, whoa, something moved down here is so weird. Okay. So that is why over here, go on. This is our V as a function of X, and my writing gone missing. So this is 50 times 10 to the power 3 multiplied by X. Okay. Right. So on this, I will stop for a bit. Anyone? Any questions, please? Anyone? Anyone has any questions? Yeah, I'm using dual screen and something is messing up. I do apologize. Maybe this dual screen thing is not working. Anyone, any question, please? I'll correct it later.
Eugene,
Yes.
have a question. Why the shear force at the right corner is going up?
The shear force in
The diagram at the right corner.
that's a very good question. You mean I add up wrongly? Wait. So what you're asking me is
The Vx.
yeah, it's going down, you mean, for this case?
I was wondering on the left hand side you said going down, but here is going up. So
this one? So you mean, so this is V as a function of X, right? So on the analysis from right to left, you mean, right?
yeah.
Because of Newton's third law, okay? Because we assume that this is coming down already, the other side has to be going what? Going up.
Okay.
Okay, does that make sense?
Yes.
Okay, so this one is also there's something wrong on. Okay, so this is M as a function of X. I wonder what's going on. No, don't worry, I will correct the notes before I send to you guys. Okay, right. Does that make sense to you now? Yes or no? Okay,
Yes.
okay, thank you. So from here, right? So now we know, right? The moment X is heading that direction. Now we know this already. Okay. So now we can start forming. So for this case, we are going to do static analysis. From left to right. Later on, okay, I will show you when to do right to left. Okay. Later on, all right, because you have to do both ways. It makes your analysis more quicker. Okay. So from here, we're going to do from left to right analysis, right? So that's where when you declare that is where you have this. Okay, you make that direction. Okay, so you have positive summation of forces in the y direction is equal to 0. Positive is going up, so you have minus 50 times 10 to the power 3 x, right? And then you have minus v as a function of x. The whole thing will be equal to 0. Okay, so v as a function of x is equal to minus 50 times 10 to the power 3 x. Okay, so this is one of our equation. Okay, so this is one of our equation. And then the next thing that we do is we have some mention about moment in the z direction at a distance x away. Okay, at a certain distance x away. So the whole thing is equal. Now, where is of interest is at this point. This is the point of interest, the red dot I've drawn, when you are doing moment. It's not at point A. It's at the dot of interest, okay, at where x stop. Okay, so from here, we have, so the moment 50 times 10 to the power 3x is going in a anti-clockwise direction. So 50 times 10 to the power 3, right? Multiply by 50 times 10 to the power 3x. Sorry. So 50 times 10 to the power 3x multiplied by a distance x over 2. Now you know why x over 2 now. Yes or no? Right? Because with this diagram, you can see better. So plus the moment about x is also going anti-clockwise. So from here, moment about point x is equal to minus 25 times 10 to the power 3 x squared. Okay. So this is the other equation. Okay. Then the next thing is, so now let's also at the same time, let me see. Let's at the same time also construct our shear force and bending moment diagram. Okay, I'm going to put a lot of things into this chart down here. Okay, so what does this, if let's look at the function now. Okay, let's look at the function now. So V as a function of x, for the shear force, right? So equation number 1, equation number 2. If you look at equation number 1, right, it's a linear function, yes or no? Right? So this is equation number 1 is a linear function, right? Whereas equation number 2 is a polynomial, second order. Right? It's a polynomial. So more or less you can guess how the shear force diagram will look like, or the bending moment diagram will look like by looking at this function. Okay. So if we look at over here, V as a function of x, let's look at equation 1. Okay, let's do equation 1. Okay, let's look at. So equation 1 is V as a function of x is equal to minus 50 times 10 to the power 3x. Okay, right. So if we were to construct, briefly sketch our shear force diagram, briefly for now, right? So if we know that this is your shear force and this is x, right? When x is equal to 0, yeah, nothing is 0. Right? We already know that already. So if we were to draw this out, this is at our point A, right? And then point A to point B, right? Point A to point B, right? Is minus 50 times 10 to power of 3. Yes or no? Right? So from here, we know that at point A, and this is what? Negative slope. Right? So when it reaches point B, it will have a negative straight line slope. So I will draw a straight line. Okay, so this is a straight line. And then at point B, right, what you see at point B, right, this is equal to what? So this is equal to minus 50 times 10 to the power 3. Okay, multiplied by a distance. So that distance is what? The distance is 0.8. Right, so minus 50 power 3 times by 0.8. So we have minus 40,000. Okay, so over here you have minus 40 times 10 to the power 3. Now, remember, equation number 1, right? The boundary is 0, x, and it has to be less than 0. What? 0.8. Okay, less than 0.8. Not at 0.8. I repeat again, it has to be less at 0.8. Right? So over here, when it's negative, right? When it's negative, right? The slope will be going in this direction. Okay, because it's negative, right? And then when it's positive, the slope will be going upwards. Okay, so just to briefly recall, you guys will know this by now. So linear function, okay, for linear parent function, Okay, for linear parent function, what we have is y as a function of x is equal to mx plus c, where m is the gradient, right? M is the gradient, c is the y-intercept, right? So positive gradient is going up and negative gradient is going down. Okay, so this is the function. You guys are, I'm pretty sure you guys this is nothing new to all of you. Okay, so now if we now look at MZ now, okay, so I'm just going to briefly sketch. Later on we'll do a detailed sketch. Okay, so if you look at equation number 2, right? If we look at equation number 2, so we know that over here is a polynomial equation, right? So if we were to sketch this out, so x, and this is the moment, and we know that at point A it has to be equal to what? 0, right? And then we want to find what is going on at point B, right? So we know that when x equal to 0 is 0, okay? So this has to be a what? The second order polynomial, this function over here is negative, right? So if we look at the second order polynomial, okay, so second order polynomial. So we have y as a function of x is equal to ax squared plus by bx plus c, right? So this is a typical function that we can see. So if a is positive, right, the graph will look like this, smiling face. If a is negative, it'll be a sad face, right? So for this case, the second order polynomial coefficient is minus 25 times 10 to the power 3. Yes or no? Right? And it has to be a set face, right? So the set face, there's only one way to draw set face, because 0 is here, set face will look like this. Okay, you cannot draw, you cannot draw, this is wrong. Okay, the next one I'm going to draw is wrong. You cannot draw a set face that look like this. Okay, you cannot draw a set face that look like oh sorry, you can also draw the set face that look like this, right? It's still set face, but why is it coming down? Okay, why is it coming down? Okay, so what does it mean that it right, both have second order polynomial, right? Both are set face, yes or no? Right? But why is it not on top and why is it on the bottom? Okay. So the next thing I'm going to teach you is based on deformation pattern. If we look at deformation pattern, so I'm going to draw deformation pattern. So this is a different color. We're going to look at deformation pattern. Right? What do I mean by deformation pattern? If the moment will generate a deformation pattern that is deforming this way, this is okay, then the moment is on top. If the deformation pattern is set face, right, then the moment has to be at the bottom. So if you look at this structure over here, if you were to look at our structure, so I'm going to bring this down so you can look at a structure. Okay, so if you look at our structure now, from A to B, can anyone tell me how the structure will deform? I'll give you two options. Okay, I'll give you two. Is the structure going to deform this way from A to B? This is plastic. This is deformation. Okay, too thick. Is the structure going to deform this way? Right. So this is deformation. Or is the structure going to deform this way? So is it the red or the pink? Anyone? The deformation. Hello? Anyone?
The pink one.
The pink one. You got it spot on. So that is why your bending moment diagram